Wait, give me a second. Let me open the presentation. Okay. Is the camera on? All right. So, hi everyone. My name is Ayah Ibrahim, and I'm a third-year medical student. And today we're going to be explaining lung. So we have 4 lectures we're going to be explaining. First off, lung physiology, intro to lung physiology, and lung volumes, lung mechanics, 1 and 2. Okay. So these are the objectives, and I usually like to put the objectives in a way that can be like answered. So first off, what's the point of breathing? How does it work? Dead space, what does that mean and why is it important? And then finally, how does the lining of epithelium change from the bronchi to the bronchioles to the alveoli? Okay, so question, and I would really love if you guys could answer either on chat or you can unmute yourself, it's fine. Why do we breathe? Anyone? Okay. All right. So the answer I was looking for, okay. We need oxygen. Yes. All right, perfect. So exactly. We breathe because we need exactly, yeah. All of you are correct, inshallah. The idea is that we need okay. Okay, so the idea is that we need oxygen for our metabolic needs. Basically, we need oxygen to supply cellular respiration, and also we need to take out all the waste products, the carbon dioxide, out of the body. So that's why we breathe primarily. Okay, so here we have to revise a simple concept, which is how diffusion works. So what I want you to understand from this slide is the particles will always move from an area of high concentration to an area of low concentration. And that's basically how respiration works all throughout the respiratory system. Okay, so how oxygen moves, it's basically what I said already, which is you breathe in air, and then the air diffuses from the alveoli into the the blood in the capillaries, and it moves to the bodies, and then it diffuses from the bodies to the body tissues. And then finally, it diffuses in the body tissues to the mitochondria, where it gets utilized for all the metabolic stuff. Make sense? Okay. So in words, the idea is that it will always move from a higher concentration to a lower concentration. And it moves from the bronchi to the bronchioles to the alveoli, and then it goes to the blood in the capillaries, and it gets pumped to the body tissues, and then it gets utilized in the mitochondria. That's all. Okay, so this is just to really illustrate the idea that the concentration, or also known as the partial pressure. So if you read partial pressure, don't be confused. Partial pressure just means concentration of oxygen. So the partial pressure is around 150 and then becomes 100, and then in the tissues it's around 40. Finally, it reaches mitochondria, which is around 1 to 2. So it just keeps decreasing the whole time. Okay. Okay, so now we just are going to be talking about the respiratory arrangement. So I want you guys to revise with me really quickly. What makes up the upper respiratory tract? So anything? Okay, the trachea, nose and mouth. Perfect. So good job, guys. You're being really active. I love that. Okay, exactly. So the upper respiratory tract is made of the nose, nasal cavity, pharynx, and larynx. And then the lower respiratory tract is made out of the trachea, bronchi, bronchioles, and alveoli. So what I want you to understand here is that the trachea is like kind of like a tree branch. So it starts as one big thing, and then it starts branching and branching and branching over and over again. We have bronchi, and then smaller bronchi, and then smaller bronchi, and then finally we have bronchioles. And attached to the bronchioles, at the end of some bronchioles, we will have alveoli. And alveoli is where the gas exchange happens. So it's basically this. where the oxygen gets diffused onto the blood, and the carbon dioxide gets diffused from the blood back to the alveoli and back to yani back outside. Okay? All right. So the upper respiratory tract also has a function which is that it conditions the air, it warms, moistens, and filters the air. And if this doesn't happen, then you can damage your lower respiratory tract where all the real like important things happens. We already mentioned this. خلاص, we're moving on. Okay, so now I want you to understand that the lower respiratory tract actually divides a lot. So it actually divides around 23 times, okay? So you have first off the trachea, and then it divides into two, the bronchi, and then the bronchi divide more and more and more, 16 times, becoming bronchioles, and then the final 7 divisions are where the respiration actually happens. Tamam? Don't worry if you don't understand this, I'll mention it again in the next slide. Okay, so the idea here is in the bronchi and bronchioles and alveoli are different from each other, and you have to know the difference. In the bronchi have cartilage and smooth muscle and goblet cells plus mucus glands, while bronchioles don't have cartilage and they don't have goblet cells or mucus glands. They only have a lot of smooth muscle and cilia. Tamam? So, like, I've seen a question before in the past about this, so just keep that in mind. And the bronchioles don't have cartilage. All right, and then alveoli is where the respiration, the gas exchange actually happens. Okay, so now we're going to be explaining a concept called dead space. It's actually really easy once you get to know it, so like don't worry about it. So the idea here, we said it divides the respiratory tract divides 16 times first, and no gas exchange happens in the first 16 divisions. Tamam? Only in the last 7 divisions will gas exchange actually happen. So the areas where respiration doesn't happen is known as the conducting zone, where no gas exchange happens, or the anatomical dead space. It sounds really ominous when you say it, like dead space, but it's actually not. It's just in the because the air isn't being utilized, that means it's dead, basically. And so when we usually breathe, we usually kind of breathe around 1 point, oh yeah, 1 point, yeah. Wait, actually, I'm just gonna revise this. Okay, so the idea here, we usually breathe around 150 milliliters, which is stuck in the anatomical dead space. 1/3 of the air that you breathe will be in the anatomical dead space. Not always 1/3, but it's usually around 150 milliliters, and this is like a number that doesn't change. Tamam? So I want you to understand that the anatomical dead space will never change. It will always be the same amount of air in the anatomical dead space. طيب? Then we have another idea that some alveoli could die, possibly, right? And if the alveoli aren't actually doing their jobs, they're not doing any gas exchange, then they're not really contributing to the respiration, and hence we will call this physiological dead space. So physiological dead space just means anatomical dead space plus the alveolar dead space. Make sense? Okay, moving on. We're done with the first lecture. Really easy. If anyone wants, yeah. Okay, thank you. Okay, so checkpoint. Does anyone have any questions? No questions? Okay. So I have a question for you guys. Does anyone want to read, or I can read? Okay. A man has a tidal volume of 0.5 liters and a ventilation frequency of 50 breaths per minute. He increased his tidal volume to 0.6 liters but kept ventilation the same. How does this affect his dead space ventilation? So how does this change the amount of air in his dead space? All right. Good job. Everyone's really smart. All of you answered C, which is correct. The dead space will always stay the same. Perfect. Okay, we're moving on to the next lecture. The objectives here are, what does a normal spirogram look like, and how can we label the four main lung volumes and capacities? Which volumes make up each capacity, and which one can't be measured with a spirometer? How do we calculate functional residual capacity using the helium dilution method, and what conditions can cause someone to have a lower than normal vital capacity? How do lung volumes change in obstructive versus restrictive lung disease? Sounds like a mouthful. It's okay. We got this. So first off, I want to explain to you that volume is a number that we can measure, and capacity is just an addition of volumes. Tamam? So can you guys just like breathe with me for a second normally? So at rest, when you're breathing normally, like not even thinking about it, this is known as the tidal volume. Okay? So the tidal volume is just the breath, the breathing that you do normally without thinking. Okay. Inspiratory reserve volume is just the volume when you're really trying to, yani you breathe the normal tidal volume, and then over that you breathe some more. So you take the biggest breath you can. Tamam? And then if you breathe out completely as much as you can, you're breathing out your expiratory reserve volume. Okay? So if you breathe out completely, like as much as you can, that's your expiratory reserve volume. An idea here is, the residual volume will always stay inside the lungs, or else your lungs will collapse. So you cannot ever expire the residual volume. You will always have volume residual in your lungs. Okay? So inspiratory reserve volume plus tidal volume equals to inspiratory capacity. It makes sense. So how much can you breathe? The capacity of how much you can breathe is the tidal volume plus the inspiratory reserve volume. And then the functional residual capacity just means how much breath is left in your lungs after you breathe out normally. Okay? Vital capacity is, oh, sorry. Vital capacity is just how much you can breathe altogether, and how much air is in your, it's just total lung capacity minus the residual volume. And then finally, you have the total lung capacity, which is everything together. طيب. So what I wanted to explain is that this is a spirogram, and you basically just breathe in it, and it measures your breath. Okay? It can measure the tidal volume, the inspiratory reserve volume, but not the expiratory, and the expiratory reserve volume, but not the residual volume. Does that make sense? Because you can't breathe out the residual volume, so it won't be able to measure it. Okay. But if you're curious, to know the residual volume, how would you measure it? So we have this method using helium gas, and basically, I don't know if you guys ever studied mole in like high school, but it's the same concept kind of, which is that the volume, you multiply. Okay, so first off, you ask the patient to breathe out completely, as much as they can. And then you attach them to this tube that has air inside mixed with helium. And the amount of helium inside is known. You know how much helium it is. When they say helium fraction, they mean the concentration of helium divided by like the amount of helium divided by the volume. So the concentration of helium in this volume. So now when you attach the person who breathed completely out, you have a known volume already in the machine, and you have a known helium amount, and you connect the patient to it. So the amount of volume increased will be the amount that they have in the residual volume. Make sense? Okay, so what happens is, the volume now is the volume of the machine at the start plus the volume of the residual volume. And the helium, when you increase volume, obviously, like imagine, okay, so when you increase volume, you will have a lower concentration of helium for that volume. So now you wanna know what the volume is, right? So what you do is, before mixing, it was you had the, what's it called, the concentration 1 multiplied by the volume in the spirometer. And now you have a new concentration multiplied by the volume in the spirometer plus the volume in the lungs. So now you want to solve for the lungs. You want to know how much the lungs, uh, okay, how much the lung itself has. Tamam? So what you do is, the volume of the lungs equals to the volume of the spirometer multiplied by the concentration 1 minus concentration 2 divided by the concentration 2. You don't need to memorize it per se, because it's kind of understandable if you like think about it for a second. Okay, wait. I'll explain again. Okay, so you have a concentration already, right? And you have a volume inside of the spirometer. I'm writing horrendously. Okay. And then you have a new volume. Okay. Will we solve this in the exam using this? You can. Probably it won't come as a question. It might come as a question, to be honest. Do you guys okay? So basically the idea is, and no, you have the concentration first multiplied by the volume in the spirometer. And then you have the concentration second multiplied by the volume in the spirometer plus the volume in the lungs. And then you solve for it. Make sense? Okay, perfect. Okay, so this is just everything we said already. Okay, so now we have a concept, which is that residual volume. So what did we say residual volume was? We said residual volume is the air that's left in the lungs after you breathe completely as much as you can. So residual volume will increase with age, and that's just a fact. There's nothing you can do about it. But the total lung capacity will stay the same. So if the residual volume increases with age and the total lung capacity stays the same, then you'll have less capacity for the lung to breathe, normal breath to come in and out, you'll have less capacity for that. Okay? Okay. Now we're going to be explaining just very simply this, which is that we have diseases that can alter how much residual volume we have. So in obstructive lung disease, for example, emphysema, you get an increased residual volume. The residual volume increases. So that just means the person is breathing in normally, but when they breathe out, it gets stuck inside. So there's more residual volume. And then the total lung capacity also increases because the residual volume increased. The residual volume increases much more than the total lung capacity. So then when we put it to a ratio, and this ratio is really important because they bring it a lot. So the ratio is that the residual volume divided by the total lung capacity, you'll find in obstructive lung disease that it increased. Now, in restrictive lung disease, the total lung capacity decreases and the residual volume also decreases. So you have some damage to the lung, and it can't hold as much air. So then the total lung capacity decreases, residual volume increases, and when you put them into when you put it into a ratio, you find out that they decreased almost the same amount, so the ratio is normal. Does that make sense? Okay. Okay. So someone asked, what is the difference between obstructive and restrictive? Let's go back. Okay, so in obstructive disease, you have a problem with the lung. It fills normally, but when you try to expire, it can't expire. It doesn't expire properly. So the air just gets stuck inside. Okay? Now in restrictive lung disease, you have a problem with breathing, with inspiring, like from the beginning, when you try to inspire, you can't inspire as much air. Does that make sense? All right, no problem. Okay. Okay, so checkpoint, how are we feeling? That was the end of lecture 2. We're moving really fast. So let's see if you guys can answer this question. Which of the following remains after maximal expiration? Okay, amazing. Amazing. All of you answered B, residual volume, and you guys would be correct. Okay. Yeah, 42 finished. Play. Next off, we're doing lung mechanics. Okay. So these are the objectives to define. It's fine, we don't need to read the objectives. You guys get it. So now I'm gonna be illustrating an idea, an important concept. The pressure outside of the body equals to 760 mmHg. طيب, that's just a fact. I'm telling you that the pressure outside of the body is 760. But because we're going to be comparing the pressure inside the body to outside the body, we just equate this 760 to 0. Okay, so because you don't want to keep saying مثلا if I breathe, okay, if I like fill up a balloon with 765 pressure, okay, and you want to find the difference between them, you just say 5 rather than 765. Make sense? Okay, all right. Okay, so now I'm going to be explaining a concept, transmural pressure. Okay, so in order for us to increase the volume of anything, I want you to imagine that the lung is a balloon. طيب, so in order for us to increase the volume inside of the balloon, we either have to fill it up with pressure, or we have to remove the pressure from around it. طيب, so in this one, we just blow pressure inside, and the pressure inside is more than outside, and that gives us the volume change. Okay? Now, in this one, what happens is, no, there's pressure inside, some pressure inside, and there's pressure outside. Then we take out the pressure from outside, and what happens in it, it expands. So the volume will change. Okay? Do you guys understand this concept? Because like everything else is related to this. Okay, perfect. Yeah, kind of. So basically, yeah, this would be like a ventilator, and this is what happens in the real body. Tamam. So what happens here is when you inhale, the diaphragm, okay, so what happens in real life is in your body is like this box. This is your chest wall, and the balloon is your lung. So when you breathe in, the diaphragm will go down and it will decrease the pressure inside of this box, basically. طيب. So if the pressure inside of this box decreases, then the lungs will inflate and they'll fill up with air. Okay? And then the opposite happens when you're breathing out. So the diaphragm relaxes, it goes back up, and the pressure around will decrease, and then you'll breathe out. Okay? All right. Moving on. So we already mentioned transmural pressure is just the difference in pressure between two things. We wanted inside minus outside. Okay? So I said okay. So basically the idea here is we're going to be talking about something called compliance. Compliance is just the change in volume divided by the change in pressure. Okay, so what happens is, if I have two balloons and I'm trying to fill up one of them and it fills up really easily and it like expands and everything's fine, then the compliance is low. No, its compliance is high. Tamam? And if I have another balloon and I'm like blowing, I'm blowing, I'm blowing, and it's like not increasing in size that much and it's really stiff, then we say the compliance is low. Okay, so compliance just means how much the volume changes with pressure. I want you to see, the compliance here, and okay, so compliance here is the most, but compliance here is the least. So the compliance is kind of related, it's directly related to the slope of the thing. So when we have a steeper slope, it means for the pressure that we're giving it, it's increasing in volume. But here, we're giving it a lot of pressure and the volume increases just a little bit. Make sense? So that means here there's low compliance, so here there's high compliance. All right. So I'll assume you guys understood. Did you guys understand? All right. Perfect. Okay. All right. So now this slide, there's a lot of confusing information about it, but it's actually not that hard. Oh, okay. Type. So the compliance of the lung, chest wall, and respiratory system. So first off, we have three components. First off, we have the lung itself, and then we have the pleura, area surrounding the lung. And then finally, we have this one, which is the chest wall. Tamam? And so first off, we said that the transmural pressure is a change in pressure from inside to outside. So we're going to be measuring the compliance of each part of the system. Okay? So first off, we have the compliance of the lung. We have the change in volume divided by the change in the pressure inside of the alveoli, you know? divided minus the pressure in the plural space هنا. Okay? All right. So what that gives us basically the compliance of the lung, like how much the volume of the lung changes with the change in pressure from here to here. Okay. Then we have the chest wall itself. So the change in pressure هنا is this part divided by the pressure of minus the pressure of the outside world. طيب, so we have the pressure in the pleura, the pleural space, minus the pressure in the pressure on the body from the outside. تمام? And since we said the pressure outside is 0, we can just say in the change in pressure, the change in volume divided by the change in the pressure in the pleural space. Yes, it's always 0. Since we said it's 700, PB is just the pressure outside. Pressure on the body from outside. We said the pressure outside is 760, but we're going to equate it to 0. Okay? Yes, it's like exactly atmospheric pressure. So good job. طيب. So then we want to know the compliance of the whole system. We don't want to know just like the lungs and the chest wall because it's one system together. They're together. You always put them together because like the lungs aren't just outside on their own. They're inside of the pleura connected to the chest wall. Get it? So the compliance of the respiratory system will be the change in volume over the change in pressure in the alveoli minus the pressure from outside. Okay, so I'll tell you why. Look at this. We have two plural pressures here. صح? So minus pleura, and then here it's pleura minus. So you can basically just cancel it out. تمام? So it becomes the change in volume divided by the change in alveolar pressure minus the pressure of the pressure on the body. So it just becomes a change in pressure, the change in volume divided by the change in the alveolar pressure. Make sense? If you don't get it completely, it's okay. We'll explain it again. Guys, do you get it? All right, perfect. Good job, guys. So, okay, so one final thing, and I'll touch on this again later, but the idea here is because, okay, I don't know if you guys ever studied physics in school, but it's kind of like resistors. Because you have two things connected to each other, you say that you have them in series, تمام? So what happens is بدل ما adding them together, you add the reciprocal of them. So this is the equation. It's 1 over the compliance of the lungs plus 1 over the compliance of the chest wall equals to 1 over the compliance of the respiratory system. طيب, so I'll just give you guys a question real quick, and let's see if you guys can solve it. So if I tell you that the compliance of the lungs is 2, and compliance of the chest wall is 2, how much would the compliance of the respiratory system be? Okay. Anyone else? All right. Good job. All of you are actually really smart because this used to confuse me so much. So basically it's 1 over 2 plus 1 over 2, which equals 2 over 2, or 1, basically. تمام? All right. Moving on. Okay, so this is just everything in words. Okay. Oh, and there's like an important concept. What's the difference between this formula and the one before it? Which one before it? Oh, okay. All right. Okay. So I think you're asking between this one and this one, صح? Okay. طيب, so for this one, they're all just the same value basically. But if you're confused between, so if هنا you have the change in volume divided by the change in pressure. هنا you have two values the compliance of the lung and the compliance of the chest wall. So if you have these two values, then you use this equation. If you have the change in pressure, the change in volume divided by the change in alveolar pressure, then you use this equation. Okay? Make sense? Okay. All right, I hope it made sense. Okay. Okay. Now this is something to come in the next few slides, but I just wanted to give you an idea really quickly. So I want you to think of the lungs as a balloon. No, this balloon always just wants to collapse. It just wants to collapse on itself. That's how the lungs behave in general. طيب, and the chest wall, which is the second component of the respiratory system. So the chest wall is like a spring. So you're trying to compress a spring, but it like wants to expand. طيب? So you'll understand why I'm saying this in the next few slides. طيب. All right, so now we're going to be seeing the curves of the compliance. Yeah, of the compliance of the respiratory system, the whole respiratory system. So, طيب. So, okay. So first off, let's start with this part, which is when the respiratory system is at rest. So when the respiratory system is at rest, معناها إنه there's no pressure. There's no pressure inside or out. There's no transmural pressure. So the pressure, the transmural pressure, the difference in pressure will be equal to 0. Okay? So this resting pressure will be at the functional residual capacity. Do you guys remember what the functional residual capacity is? We said it's when you're breathing normally and you do the vital, tidal volume. You breathe out the tidal volume and you're left with the functional residual capacity. So this is when you breathe normally. طيب, when you expire normally. Okay, so what I want you to see here, and the compliance here is the most. So breathing is super easy at this part. And then breathing out is also super easy. Okay? Now, هنا, you can see that what's it called? Yeah, you can see that the curve is, yeah, it's kind of flat, and that's why you can see that, sorry, I'm losing it. Okay, so here we have low compliance. So here we have low compliance because the curve is flat. And that's why here, like when you reach خلاص, the total lung capacity, like you stop breathing because like it becomes hard after this. But here you stop when you reach residual volume because it becomes also hard after this. That's all it can reach. Okay? Makes sense? And we said the compliance of the respiratory system, arterial pressure, alveolar pressure. So someone asked if the transmural pressure is 0, how's the compliance greatest in this area? Since compliance equals to volume. Oh, okay. I get what you're saying. So it's not that, okay. What I meant was in the compliance hina is easiest because the compliance hina, look at if you see the graph, not here, sorry, it's here. And no, hina, the graph is like super, like it's, what's it called? And no, the graph is like, it's not perpendicular, it's like kida, okay? So what the idea is that here you will have, all right, so here you'll have the greatest compliance because, yeah, steep, thank you. Okay, so here it's so steep, and that means the compliance with every pressure, the lung volume is changing a lot. So look at this. You're increasing the pressure by like 2, and look at how much the volume changed in that amount. Compared to مثلا هنا, if you increase the pressure with a little bit, the volume isn't increasing that much. Make sense? All right. Okay. Okay. So now we're going to be comparing the compliance of each part of the system. First off, we have the compliance of the lung. Tamam? So if you check out the compliance of the lung, you'll find that the lung wants to always collapse. It wants, this is its resting volume. So if we put it, no, type, if we let the lung go back to zero, if we let the pressure inside become zero, then it wants to go back to its resting or minimal lung volume, which is below the residual volume. طيب. And you also see that at total lung capacity, the graph is least steep, and that's why there's the least compliance here at the total lung capacity. All right? Does that make sense? Okay. All right. طيب. So now we're going to be talking about the compliance of the chest wall itself. We said the chest wall always wants to expand. It's kind of like a spring. It always wants to expand. So it wants to be at this part. It wants to be at this point, which is between the functional residual capacity and the total lung capacity. It's around 60% of the total lung capacity. So basically, it just wants to be here. And also, its lowest compliance is here, around the residual volume. تمام? So it wants to be here, and هنا is where the like highest compliance you can see how steep it is. هنا the highest compliance, and هنا the lowest compliance. So it never wants to reach residual volume basically. تمام? Okay. So the idea هنا is إنه the actual respiratory يعني compliance curve is kind of a balance between the lung compliance and the the lung compliance and the chest wall compliance. So it's a balance between both of them. All right, so the lungs want to collapse, but the chest wall wants to expand, and that's why they reach a balance, which is the respiratory compliance. All right. Okay. So that's just the idea here. Okay, so now we're going to be explaining an idea, pneumothorax, which basically just means if the pleura is punctured, we said the pleura is what holds the lungs to the chest wall, right? So it's what holds everything together. But if the pleura, like the pressure in the pleura increases and it becomes within zero, the same as the lungs, then the lungs will just shrivel up and the chest wall will just expand. Okay? So if you don't have the pleura holding them together and balancing them out, this one will just shrivel up and the chest wall will just expand, and that's it. Like there's nothing you can do about it. So what we have to do in pneumothorax, it usually is like something like a bullet wound or something, and it punctures the pleura. Then we have to take out the air manually. We just suction it out, and then it returns back to normal. That's the first thing we do. So that's the idea here. You puncture the pleura, and then you take out the air, and everything will be okay. Make sense? Okay. All right. So now we're going to be explaining breathing cycles. What did we say happens when we're inspiring? What happens to the diaphragm? Does anyone remember? Okay, so exactly. So we said that the diaphragm goes down, it contracts, and it decreases the pressure in the pleura. So if the pressure in the pleura decreases, exactly, it creates a negative pleural pressure. What happens is the transmural pressure in the alveoli would also, there will be a net decrease. طيب? So now that allows us to breathe. We take in air. When that happens, all of a sudden, خلاص, we breathe in. Okay? So now what happens is at the end of inspiration, the air inside of the alveoli, خلاص, it's like zero. And it's the same as the outside pressure, basically. All right. So now the diaphragm starts to relax and it goes back to place. So when it goes up, the pressure, what happens to the pressure inside of the pleura will increase. Tamam? So when the pressure in the pleura increases, the pressure in the alveoli, the transmural pressure also like changes. And then the person breathes out. So the air inside of the alveoli will become too much, and it's too much pressure inside of the alveoli compared to the pleura. And then the person breathes out. Yes, exactly. Negative pressure for inspiration and positive for expiration. And then it happens again. So at the end of expiration, the diaphragm again just will contract and the pleural will have a negative number, and then the cycle restarts. Make sense? Okay. All right. So now we're going to be explaining changes in compliance with lung disease. So this is the normal compliance curve. And then an emphysema or obstructive lung disease. Do you guys remember that we said in the previous lecture that emphysema is an obstructive lung disease and fibrosis is a restrictive lung disease? So in obstructive lung disease, specifically emphysema, what happens is you have an increased compliance of the lungs. So I want to explain to you a simple idea, which is recoil. So imagine you have a balloon. Once you blow into the balloon and it increases in size. If it increases in size easily, we said, this is high compliance. صح? But if it increases in size easily, it probably won't go back to its size like quickly. You know what I mean? Because it has high compliance, the recoil is low. So compliance and recoil are opposite, like two opposites. They're reciprocal of each other. So if you have increased compliance, you have decreased recoil. Make sense? So in emphysema, you'll have increased compliance, but when you try to breathe out, the recoil is low. And that's why you'll have an obstructive lung disease, which means the air is trapped inside. It won't come out. Okay? And then for fibrosis, on the other hand, you have a problem with breathing in to begin with. You're trying to breathe in and you're trying to fill up, but there's low compliance because the tissue of the lung itself is like damaged. All right? So you'll have a low compliance and probably high recoil. How did emphysema increase compliance? Okay, so I'm not sure how emphysema increases compliance. I just know it increases compliance because there's like so much volume inside of the lungs itself. So if you're breathing in, the volume is increasing a lot, and you're only like the pressure isn't even that much. Make sense? All right. Okay. So now we're just going to be explaining the breathing cycle again. And this used to confuse me a lot, but it's actually really easy. So the idea here is the volume. When you're breathing in, the volume increases. And then when you're breathing out, the volume decreases. صح? So for alveolar pressure, when you're trying to inspire, first off, you have to have a really low pressure in the pleural. And that's why the pleural pressure decreases and then the alveolar pressure decreases with it. And that's when you have inspiration. And then at expiration, your alveolar pressure is high compared to the outside, and then you breathe out. Make sense? So pleural pressure all throughout, it just decreases until the end of inspiration, and then it increases with expiration. All right. Okay, so we said the volume will increase with inspiration, and then it will decrease with expiration. Okay? Okay. So expiratory flow just means how much you're breathing out. You're not breathing out, you're breathing in, so it goes down. And then when you're breathing out is when the level will be high. Tamam? It just means how much you're breathing out at that second. So when you breathe out, you usually breathe out like a lot at the beginning, and then you like taper out the breathing. You know what I mean? Like you breathe out, and then at the end, the breath is like less by the end of it. Okay. And then alveolar pressure, we said that the pressure will decrease, and that's when inspiration will happen. So when inspiration happens is when the breath is decreased. And then when the alveolar pressure is high is when expiration will happen. Okay? All right. Okay. So that's it. That's 3 lectures. We're doing the last lecture now. Okay. Okay, so this is a new concept, which is that the compliance of the lung is determined by 4 things. First off, we have the elasticity of the tissue. And then we have something called the principle of interdependence of alveoli, we have surface tension and then surfactant. So let's start with elasticity of the tissue. So I already explained this to you kind of. It's kind of a new concept, but it's also kind of not. We said elastic recoil is the opposite of what? Do you guys remember? Yes, perfect. Compliance. Good job, everyone. So we said elastic recoil is the opposite of compliance. So when elastic recoil increases, the compliance will decrease. Like, so the lung has both. It has compliance and it has elastic recoil, and that's why it can expand and it can also return back to its original shape. And this is a really important concept because you don't want it just to inflate and stay like that. You want it to actually go back. All right. Right. So now this is a new concept. It's called the interdependence of alveoli. So I want you to think of alveoli kind of like bubbles, right? Like, so what happens is that they're all sharing one system and they all have air inside of them. So if you compress one bubble, it'll kind of blow its air into the other bubbles, right? The other bubbles will increase in size to compensate for this one becoming smaller. Okay? But the thing is, once you blow into the other bubbles, their compliance decreases with increased size. So if they're increasing in size, their compliance decreases, and they're all interconnected together, so they push back the air into the alveoli that was pushing the air originally into the others. So one more time. If one alveolus started to get smaller and pushing the air into the others will, their walls will stretch and they'll all accommodate each other and return back to normal. Tamam? Does this make sense? Yeah. So if one gets smaller, the others will expand, but the thing is, with expansion, their walls will stretch and they all share the same walls. So then they'll push the air back into it. So, all right. So that's basically the idea. And one of them will become smaller and then it'll push the air into the others, and then the others will just push the air right back. Okay. And that's how we maintain the size of alveoli, and the alveoli don't collapse because we don't want them to collapse, obviously. Okay. Okay. So now a new concept. I think you guys already know this, but we're going to be talking about surface tension. So surface tension just means that liquids, when they come in contact with air, they don't want to come in contact with air. You know how we say things are hydrophobic? These are like aerophobic. They don't want to come into contact with air, and so they push into each other and they push to the sides of each other, and they just try to avoid the air as much as possible. And that's the idea here. It's the tendency of liquid surfaces to shrink to the minimum surface area due to cohesive factors. Play it. So you can see all of the liquid particles are attracted to each other, but they're not attracted to the air. And that's why they push into each other and they try to avoid the air as much as possible. Okay? Okay. All right. So Hina, it's just a hypothetical situation, which is, imagine if you were inflating your lungs with water instead of air. What happens is the compliance would be so much higher and it would be so much easier because, as we said, the water likes each other, but it doesn't like air. So what would happen, it would fill easily and no surface tension would happen. And the compliance would be really easy. It'll just fill up. Okay? But when inflating with air, the compliance isn't as high. It's not as steep as this one. So that's because the surface tension, what's it called? The alveoli are made to a large extent of water. And so they push away from the air and they don't like interacting with air. And that's why the compliance will be low. Make sense? Okay. Okay. So now we're going to be talking. Yes, exactly. So someone said it's easier to inflate lungs with water than air because they're the same medium. Exactly. Because the alveoli are made of water to a large extent, when they come in contact with other water, they'll fill up easily. But if they come in contact with air, they'll try to push the air out and they won't fill up easily. Okay? All right. So now we're going to be talking about something called surfactant. So if you guys ever heard of surfactant, you'd know it's like it's not just in lungs, it's just a chemical compound that lowers the surface tension between two different phases. And we said the two different phases in this example is liquid and air. Okay? So these are the things that surfactant can do, and we don't know any of them yet. So let's get into it. Okay, so basically, first off, without surfactant, we'll have to explain something. It's called Laplace's law, and this is just a law. Like you can't really do anything about it. It's just a fact, which is that pressure will increase in smaller alveoli. So if you have a smaller alveolus, the pressure inside of it, when air comes inside, the pressure inside will be more. Tamam? All right? So that's just a fact. And no, inside smaller alveoli, the pressure will be more. And we said the pressure always moves from an area of high pressure to an area of low pressure. So these smaller alveoli have a tendency to collapse. They move the air from inside of them and they go to the bigger, they move the pressure from inside of them to bigger alveoli, and that's what happens. Basically, they just collapse. Okay? So what happens when we have surfactant? It lowers the surface tension. So here in Laplace's law, you can see that the surface tension is basically how pressure increases. So if we have more surface tension, we have more pressure. So if we decrease surface tension, we'll decrease the pressure, and then the alveoli probably won't collapse. Right? And it also increases the compliance of the lungs. It minimizes collapsing tendency of alveoli, and then it reduces the pressure difference between the alveoli and produces alveolar stability. So because it makes the pressure in the small alveolus similar to the pressure in the big alveolus, and so the pressure won't move between them. Make sense? Okay. All right. So we said that surfactant will decrease surface tension. And now we want to understand how it decreases surface tension. So this is surfactant, and it has basically two sides. It has a hydrophobic, yeah, hydrophobic tail, and then a hydrophilic head. So the hydrophilic head will like hang out with the water molecules, and the hydrophobic tail will like interact with the air. Tamam? And this decreases surface tension because it creates like it creates a pull to the air. Yeah, kind of. It's similar to it. Tamam? So it creates a pull to the air, and it makes the water like interact better with the air rather than forming surface tension. The surface tension is decreased to a large extent. Because we said in the surface tension happens because the water is attracted to each other, but it's not attracted to the air. But then the surfactant is attracted to the water and the air. And that's why it decreases surface tension. Make sense? All right. So we said surfactant reduces surface tension and increases compliance because we said surface tension will decrease compliance. So if we have reduced surface tension, we'll increase compliance. Okay? Second off, we said surfactant minimizes fluid accumulation in the alveolar space. We actually didn't talk about this yet. And then we have surfactant helps keep the alveolar size relatively normal during the respiratory cycle. So this is the third point, which is no. Okay, so what happens is if we have two alveoli, right? So they're originally the same size, and if مثلا one of them fills with more air, then the surfactant, the concentration of surfactant will be less. So when the concentration of, we said when surfactant decreases, what happens to compliance? Does anyone know? Okay, so we said, okay, so all right, perfect. I'll repeat the question. So we said, no, if surfactant decreases, what happens to compliance? Exactly. So surfactant is related to compliance, and if surfactant increases, compliance will increase. And if surfactant decreases, then the compliance will decrease. And the idea here is because surfactant decreases the surface tension. تمام? We said in a surface tension decreases compliance. Make sense? All right. Okay. So the idea is if we inflate one of them more than the other, what happens is surfactant will decrease, the amount of it will decrease. And so the compliance will decrease. And that's why the alveolus will be like, no more, don't fill me up anymore. And the air will instead go to the area with least resistance, and it will increase in the other areas that have more compliance. Okay? Does that make sense? So I'll just explain one more time. So here the air is coming in, and then when it comes in, we said, if the amount, so the concentration of surfactant will be decreased here because there's so much air. So then when the concentration of surfactant decreases, you'll have less compliance. And so it'll push back the air. It won't push it back in. It will say like, no more air. So the air will instead go to the area with easier compliance. The area where there's more surfactant and it's easier to fill up, and this is it. Okay? Yeah. So that basically happens until they become the same size, and that's why surfactant is so important. So like not some of them collapse and some of them fill up. It's better to have them like all similar sizes. Okay? Okay. All right. So we're going back to this point, which is that surfactant minimizes fluid accumulation in the alveolar space. So the idea here is that basically surfactant will decrease. Okay. All right. So the idea is but actually, I think it's the next slide. Yeah. Okay. So the idea is if surfactant fills up, so when surfactant fills up the alveolus, what happens is if, okay. All right. So if the surfactant fills up the alveolus, then the surface tension will decrease. And that will minimize the amount of water that comes into the alveoli from the interstitium. You guys know that law that says, like oncotic pressure and all of that, like water drips from the interstitium to other places where there's like lower water. Okay. Type. Let me just check that real quick. Okay. All right. So yeah, basically, it decreases the. Okay, yeah. So what happens, it decreases the inward pressure. All right. So sorry, I got it now. Type. So what happens in a surfactant decreases the amount of uh. Okay. Type. All right, so we're on the last few slides. خلاص, we're about to finish. We just said inner surfactant minimizes the fluid accumulation in the alveolar space, and this happens because it basically reduces the amount of pressure inside of the it increases the amount. Okay, so what happens is if there's no surfactant, the alveoli are dry first off, and second off, they have like a tendency to collapse. تمام? So if they collapse, they will bring fluid inside of them. تمام? So what happens they pull because of the lower pressure. If they collapse, the lower pressure inside of them will pull the fluid from the interstitium into them, and that's what happens. So if we have surfactant, that doesn't happen. There's like no spaces for the fluid to come in, and that's why they basically they won't have any fluid accumulation from the interstitium. Tamam? So we already covered this. We said the 3 points, which is inner surfactant reduces surface tension and increases compliance. It minimizes fluid accumulation in the alveolar space. And then lastly, it helps keep the alveolar size relatively uniform. And this is really important for ventilation among alveoli. Okay, so we covered this. Now, this is for the sake of completion, even though you're probably going to cover this also in histology, which is that alveolar epithelial cells type 2 are the ones that secrete surfactant. So it's not just any type, it's the type 2. All right, and then we have, so we have, like, we can get rid of surfactants in 2 ways, which is alveolar macrophages, or the type 2 cells recycle or destroy the rest. This isn't really important. Khalas, that's all, we're done. So now we're going to be moving on to the questions, and those are all 4 lectures. Okay. All right. So if someone can see the chat and answer, because I can't see the chat locate. All right, so it says a patient was asked to exhale maximally and then was connected to a spirometer containing 10% helium. The volume of the spirometer was 5 liters, and after rebreathing maneuver, the helium fraction approached a steady value of 0.08. Now, what is the calculated residual volume of the patient in liters?
Someone asked C.
B?
C.
C? All right, perfect. You guys would be correct if we went back to the slide. It's actually the same. I got this from past papers, and it's exactly the same as the slides. So if that makes you feel better, inshallah, look at you the same question. So, all right. So it's basically this. And all right, so the pressure inside first off was 1, and then what's it called? It was 0.1. And the volume in the spirometer was 5. صح? And then after mixing, the pressure, the concentration becomes 0.8, and we have that the volume in the spirometer is still 5. صح? Plus an unknown number. All right? So if we're solving for this, it's just this equals to this. So it's 0.5 equals to 0.8 multiplied by 5. And it's not 0.1. It is 1. So it's 5. Tamam? And I don't have a calculator for this, but like you can do it easily. So it's just going to be x equals to 5 divided by 0.8. صح كده? No, it's going to be 0.8 multiplied. Yeah. Wait, I'm confused. Okay, a second. It's going to be basically the x will equal to the 5 multiplied by the change in volume. So it's going to be 1 minus 0.8 over 0.8. Make sense? All right, so moving on to the next question. A patient was asked to exhale maximally. Oh, it's the same question. Type. What is the effect of increasing surface tension? Guys, pretend you didn't see the answer. What's that? What's the answer? So we said surface tension of increasing surface tension, it will decrease lung compliance. And we said that increasing the surfactant will increase lung compliance. صح? And we said increasing surfactant will decrease surface tension. Make sense? طيب. Finally, we have the last question. Which of the following is illustrated in the graph showing volume versus pressure in the lung chest wall system? Okay. So the answer is D. It's that when the airway pressure is 0, the volume of the combined system is the functional residual capacity. And we already said it in notes here. And when the respiratory system is at rest, it's going to be at the functional residual capacity. So does that make sense? All right. Thank you guys for being here. That's the end of the lecture. Thank you so much. And please fill in this form. And if you have any suggestions, feedback, just go on and say it. Sorry. Thank you. If you have any questions, don't hesitate to ask. Have a good day.